Alright guys, so today we're talking about chemical reactions, starting our new unit. And this is really start to get a lot of fun, I think, in the course. So let's go ahead and get started. It's very important that you remember the 7 diatomic elements. We've talked about these before. Just remember the H, N, O, F, Cl, Br, and I. Those elements, if they are written in an equation and they are an element, they're not part of the compound, you must have 2 of them together. So just remember those. So you can get them on the table. They actually draw a little 7 on the table. There's 6 of them plus the hydrogen. Remember those 7 diatomic elements. Okay, very important. All right, so moving on, let's introduce reactions. Just in general sense that chemical reactions are occurring around you all the time. So I just want you to realize that even though it seems like they're not important, chemistry sometimes seems like, oh, I'm never going to use chemistry, and you may not. Reactions are a moment by moment part of your life, whether you realize it or not. I mean, just even in your body is a just massive amount of chemical reactions that's occurring. And so digestion is one simple little example of many chemical reactions that are occurring during digestion. Photosynthesis, another example. Plants producing oxygen gas, producing their own sugar for their own energy use is another example. So all the time, decomposition, everything, all things, all kinds of chemical reactions occurring around you all the time. Chemical reactions occur, here's your definition effectively, they occur when elements join, separate, or rearrange themselves. And so to do so, chemical bonds have to be broken and reformed. And that breaking and reforming of the chemical bonds, that is the chemical reaction. And so anytime these elements join, separate, or rearrange themselves, chemical bonds are being broken and formed, and those are chemical reactions. A very important skill for you to be able to do is to be able to take a sentence of a chemical reaction and convert that sentence into a formula-based chemical equation. And so that's what we're going to be mainly doing today. The chemical equation, that formula-based chemical equation, is simply a representation of a chemical reaction. That's what a chemical equation is. It represents on paper the chemical reaction that occurs in the vial, test tube, whatever, wherever that's occurring. The basic form is that the reactants are on the left and the products are on the right. The arrow that separates the reactants and products, you can read that as to form or to produce or to create maybe, but that's going to be your dividing point. An important thing to understand that sometimes is lost on students is that you really this is also a time divider, if you will. This is the before and this is the after. Sometimes that's lost. Sometimes students think that these two things exist simultaneously, and there very well maybe some reactants left over and some products when the products are produced. Maybe some of this left over, but the main idea is that these things are turning into these things, and so it's a before and after look at what you have. So that's something to keep in mind. So let's practice writing a skeleton equation, and we'll define a skeleton equation here. It's basically an unbalanced chemical equation, and I know you've had a little bit of practice balancing equations, but we're going to do a lot more in the next few days. But anything that's unbalanced is a skeleton equation. And so an example would be this, the reaction of hydrogen gas. So hydrogen gas is a diatomic element, so we're going to write it as H2 because it's by itself, and it's going to react plus or with something else. So that's our plus sign, if you will. And then it's going to combine with oxygen gas. So let's write the symbol for oxygen gas. That's going to be O. Since oxygen's diatomic, it's O2. It's going to produce, so that's our arrow. So these are our before. We have these two things beforehand, and then after they react, we produce something new, and we're going to produce water in this case. And we all know the formula for water, which is H2O. And so that is a skeleton equation for the sentence. So the sentence, the reaction of hydrogen gas plus oxygen gas to produce water, is represented by the chemical equation H2 plus O2 produces H2O. Again, skeleton equation because it only shows the bare bones. It just shows the reactants and the products. We don't balance the equation. It doesn't show the ratios, which is the balancing aspect of it. All right, another example, dicarbon hexahydride reacts with oxygen to form carbon dioxide gas and water. So the dicarbon hexahydride here, there is an organic name for this. We're not going to worry about that right now though. So we'll just use this as our naming, regular old naming that we've learned so far. So that would be C2H6, dicarbon hexahydride. It's reacting with, and so that react with can be symbolized as the plus sign, and then it's going to react with oxygen. Now oxygen, once again, it's diatomic, and so when you write that symbol you're going to need to have an O2, and it's going to form, again, that's our indicator of an arrow sign. To form is our arrow, or to produce. It's going to produce carbon dioxide gas, so carbon dioxide is CO2. And it's also going to produce water, which is H2O. So again, there's our skeleton equation. Once again, you can see that it's not balanced. You can see right away we have one carbon here, we have two carbons here. That's not balanced, so therefore this is a skeleton equation. You also have the reactants on the left and the products on the right. Once again, just remember the reactants react to produce the products. So the reactants react on the left side to produce the products on the right side. Some additional symbols that you're going to need to know to write a more detailed chemical equation are the states of matter symbols. And so they are solid, liquid, gas, so S, L, G. And then a fourth one, AQ, stands for aqueous. So let's just do a real quick explanation of these. If you have, for example, H2O-S, H2O-L, H2O-G, well, H2O-S would be what? It would be ice. H2O-L, that would be your liquid water, like you would drink. And then H2O-G you might call that steam, although that's not technically correct. Steam, gaseous water, just water that's in the gaseous state, would be H2O-G. And so AQ is different. A lot of times students have difficulty with AQ. AQ, or aqueous, means dissolved in water. Okay, and so an example of that might be this. If you have NaCl, S, well, that's just salt like you have on your table that you put on your food. If you have NaCl, L, that's going to be liquid salt that's been melted, raised to a very high temperature. If you have NaCl, AQ, well, that's salt water. That is salt that has been placed into water and it is dissolved. It is still salt, it's just dissolved in the water. So anytime you see AQ, that simply means dissolved in water. Sometimes students think that it means it is water or it's liquid. It just means it's been dissolved in water. An example reaction using all of the terms. So you can see here we have zinc, and so that's Zn, but it's been said it's indicated as a solid form, so you put the little S after. If there's no indication, you just leave that area blank. It's reacting with, so that's the plus sign, aqueous hydrochloric acid. So if you remember your naming system for hydrochloric acid, you ought to get HCl out of that, or if you just memorized it. So HCl, and then the aqueous, so AQ. Most all of our acids we're going to dissolve in water to make them useful. Produces, so that's your arrow sign, hydrogen in the gas form, so H2G, and zinc chloride in the aqueous form, so ZnCl2 in the AQ aqueous form. And so that's an example of a more complete description of a chemical reaction. Oftentimes we'll leave off the state symbols. We're not doing, those are important when you start doing energy reactions, figuring out how much energy is involved in the reactions, but right now they're not too critical for us. Some additional symbols. A lot of times you have to add heat to a reaction, and so we have symbols for heat. We also have a symbol for a catalyst. So if those are used in a chemical equation, we can indicate that as well. The heat symbol is the triangle, and it's placed on top of the arrow in the to produce. So like right there, you put the little triangle over the arrow. The catalyst, you would use the formula of the catalyst and you would place it over the arrow as well. And so let's look at an example here. So Al2O3, aluminum oxide, can be decomposed to produce aluminum and oxygen. And so if you want to get the aluminum metal out of this oxide, this ore, then you can just heat it and get that out. So we need to put the symbol heat over it to do so. A catalyst example would be the decomposition of hydrogen peroxide, H2O2 is hydrogen peroxide. You have that in your bathroom in your little brown bottle. We've talked about it many times before. That will naturally, normally decompose to form water and oxygen. Water is a more stable combination of hydrogen and oxygen combined than hydrogen peroxide. This is not very stable, so it decomposes to a more stable form of a compound with hydrogen and oxygen. That's why it's stored in a brown bottle. The light can speed that decomposition up. If you have a really, really old, multi-year-old bottle of hydrogen peroxide, there may not be very much hydrogen peroxide left in there. But anyway, we can speed this reaction up if we want to. Sometimes we may want to because we can produce oxygen, which sometimes we have fun with that in experiments. And manganese dioxide would do that. It would speed it up rapidly. And so MnO2 is the formula for manganese dioxide. You can place that over the arrow, and that means that it is a catalyst. Remember, catalysts they speed up reactions, but they are not changed. They are not part of the reactant or product because they're not changed. You have MnO2 going in, and you have MnO2 coming out. It's unchanged, therefore it's not a reactant or a product. It's a catalyst. So let's do one more example. So solid glucose reacts with oxygen gas in the presence of heat to produce liquid dihydrogen monoxide and carbon dioxide gas. So the little words are going to spin as a symbol comes up. And that's the connecting point, if you will, ties them together. So for example, glucose, and there's your formula for glucose, C6H12O6. It's the solid form. And so the solid glucose, we'll put an S after it, is going to react with, so that's a plus symbol. It's going to react with oxygen gas, so oxygen, O2, and gas, G, to produce, that's our arrow, but it's going to do that in the presence of heat. And so in the presence of heat will be symbolized by the triangle, and it's going to produce liquid dihydrogen monoxide. So dihydrogen monoxide is just water, and it's in the liquid form. And we're going to produce carbon dioxide in the gaseous form. And so that's a very descriptive chemical equation, telling you a lot of information. And so that's where we're going to end today. You're going to do some practicing, some running some equations. Again, the nomenclature is important. Remember, and diatomic elements is important. And so we're bringing a lot of stuff in from old, and we're putting it down on paper. All right, that's it.